SwayamPrabha. Digital India. Educated India.
Hello and welcome to this class on industrial robot design and applications. In the last class, what we looked at is the mechanical manipulator design, mechanisms design. And we saw that when you design a robot, you should keep various things in mind. For example, the degrees of freedom, then the manipulation ability, then the dynamic manipulation ability, then look at the workspace, the load carrying capacity, then also compute the structural index of the manipulator before you decide what is the kind of robot you're going to buy or you're going to design. From the kinematics point of view, it is very important to understand about the existence of a solution and how many solutions are there, which solution are you going to take. So these things are aspects which you need to keep in mind when you're designing a robotic mechanism or a robotic manipulator. And today what we'll be looking at is industrial applications of robots, and then further we'll proceed to programming of robots in Val 2 in the next two lectures, which are going to be our last. So today we'll look at applications of robots in industries. Now, with whatever you have studied so far, a very interesting question comes to mind is where should robots be used? Can you use robots everywhere? Okay, it's like saying that you just buy a robot and use it somewhere. Now, that question is basically more to do with economics than to do with technology. Technology, yes, but more to do with economics. Now, the technical part of it is that there are some jobs which robots cannot do. So if I were to ask the question that what kind of jobs a robot cannot do, you have to think with whatever you have studied in terms of kinematics, dynamics, and try and come up with answers as to what kind of jobs a robot cannot do and why it cannot do. Okay, so we'll proceed with today's lecture on industrial applications and the future of robotics. That in terms of industrial designs, what is that people are looking at now in terms of applications of robots in industries. So today we are having the class on industrial robot designs for welding, painting, and robot safety, and we'll see also that in the future what kind of robots are being targeted for industrial applications and why. So this question of why is something which is very, very important, and we have to keep it in mind as we go ahead. Now, the current applications of robots in different industries are majority of the robot applications, almost I would say 80%, are in automobile and industrial electronics. Now, in automobile industries, it is where robotics started off, where robots were used for things like spot welding, spray painting, assembly, pick and place, and with the increase in the electronics industry now, in terms of electronics, right from consumer electronics to industrial electronics to defense electronics, something like a refrigerator, TV, smartphone, a laptop, okay, a tablet, everything is assembled by robots. So you have a motherboard and the various parts or the chips and various connections onto that are made by robots. So 80% of industrial applications are in automobiles and electronics industry. Then we have space applications, where now space, we understand that human beings cannot go to space. Okay, so as a start, what is done is robots are sent right to Mars, and you're familiar with the various Mars rovers which are on Mars exploring the surface of Mars. Then we had lunar rovers. So space application is another area where people have to use robots, because human beings it's not very safe for humans to go and explore space. The other is defense application. This is something which is coming up extremely fast now, and a lot of the robotics companies are focusing towards defense applications, because in most countries they would not like their soldiers to come to harm on the battlefield. Okay, and so it's a very good option to send a robot in place of a soldier. That is one. The second is unmanned applications like unmanned aerial drones, okay, underwater unmanned vehicles. These are applications which are coming up very, very fast, and because of the advancements in particular technology, we are having new applications almost every day. So defense is another place which is coming up, probably the fastest growing. If I were to say the fastest growing, then the fastest growing is defense. Okay, so fastest growing would be defense sector in robotics. Space applications was always there, and atomic energy. This is where robotics started off. We said that the robot actually took birth when they were making the atom bomb in 1940, 45, 46. And that is where the master-slave manipulator came up. And even today, in atomic energy establishments, the master-slave manipulator is used because it is a dangerous place for robots. So current industrial uses of robots are in these areas: automobile, electronics industry, space, defense, atomic energy. Now, over the years, this industrial robotics companies are more or less saturated, in the sense that there are standard companies, and for a new company to come up or a new application to come up, it's extremely crowded space now. So the new industrial application or non-industrial applications that have come up, so these are under non-industrial applications that have come up recently in the past. One is rehabilitation, okay, then healthcare, prosthetics, entertainment, pets, movies. This is a very, very big business today. Okay. So we have current industrial applications, we have non-industrial applications. And then what about the future? The future is general assembly, rehabilitation, healthcare, personal robots. Social robotics is one big issue in the future. So what I talked about in the last class is how to design aspects of the standard industrial manipulator or a robotic manipulator mechanism. Today we'll see other aspects where robots are being used and what is the future of robotics as far as industries is considered. Okay. So this is a very interesting slide called the rise of the machines. Now, when we're looking at 2016, which is still 4 or 5 years ago, it is basically seen that the number of robotics applications being installed across the world is rising very, very fast. Okay. And China obviously seems to have the largest number of robotic installations across all countries, followed by South Korea, North America, Japan, Germany, in that order. Okay. India is still very small, but India is also coming up in terms of robotics applications in various industries. Now, the graph on the right is also interesting, that the number of AI patents being filed, okay, which has to do with robotics, is till now it is the highest in the US, but China is catching up fast, and it is expected that in the future this graph, if I project it like this and if I project this like this, it is going to meet somewhere. Okay, so the left side graph shows the number of robot installations year-wise. The one on the right shows the rise of machines, or what is called the AI patents, filed across the world. Now, one of the reasons of this new aspect of robotics which has come in, or social robotics, is the aging population across the world. Now, with an aging population, there is less of people to do manual jobs, and even jobs like teachers in kindergartens, in elementary schools, it's difficult to find teachers. So this is where robotics is coming in a very, very big way. And in the present scenario of the worldwide pandemic, again, robots are the safest bet. So robots have found a new avenue of robotics industries in this current pandemic situation. For robots which are going into healthcare, robots are going into medical applications. Now, in terms of the aging population, you can see it is Japan, Korea, Thailand in that order. And very interestingly, India is also there, right in the middle there. So with the life expectancy increasing in so many of these countries, there is becoming a great demand for, one is healthcare, one is rehabilitation. Okay, rehab is one. Okay, then in terms of social robotics. So these are aspects which were not there maybe even 20 years ago, but now this is probably going to take over the robotics industries, apart from the industrial robotics of automation in automobile industries and electronics. Now, robots per year, this is a little old data, but it shows that the number of robots per year is increasing every year. Okay, we saw this was a more recent data, 2016, that China has the fastest growing installations of robots across the world. Now, very interesting question would be that what about India? Okay, what about developing countries? Now, what we see here is that why is the number of robots increasing every year? Of course, in pandemic, we understand that human contact is to be avoided. But with a growing population, again, we understand that for rehabilitation, we need robots because people are not there. Younger people are not there. But the major cause, the major reason is that essentially in 1970s, we had we talked about the second revolution, and after the second revolutions, what happened is the electronics became smaller, cheaper, and faster. So it is electronics, okay, becoming smaller, cheaper, and faster. Okay, and this is what exactly uh, gave rise to this graph, which is showing that the price of the robot is actually coming down because electronics is becoming smaller, faster, cheaper. Today, you can buy a good industrial robot with a very fair, the 10 kg payload capacity with about 20 lakhs, which was not possible maybe 20 years ago. Now, on one side, the price of the robot is coming down. On the other side, the price of the labor is going up. So if a company has to survive, then basically there is no other way but it has to go in for automation and use robotics. So also, although in India we tend to say that there's a lot of population in India, okay, the second highest number of people in the world, but even for Indian companies to survive in the international market, then they have to implement robots. There is no way out here. Now, as we proceed further, what are the new areas in which robotics has come? This is a very interesting question because industrial robotics space is more or less dominated by the major companies like Hitachi, Fanuc Robotics, then Yaskawa Robotics. So for a new company to come into that space is extremely difficult. But the other non-industrial applications of robotics have come up. And these non-industrial robotics applications are in many, many areas. For example, underwater cleaning, defense, rescue, security, construction, field applications, mobile robot platforms, medical, logistics, all others. Okay, so this is an area where suddenly there is a lot of new companies coming up and a lot of new business opportunities. Now, when we talk about these robots, their design would be different from that of standard industrial robot design or manipulator designs. Okay, as we go along, we'll try to see what are these new designs which are coming in and what are the new requirements for industries that are coming up. So, non-industrial applications of robots, service and entertainment. This is a very, very big area again. Even in India, it is surprising that this is a very big area. So, in service and entertainment, we have vacuum cleaners. Okay, Eureka Fob already has automatic vacuum cleaners. So, these vacuum cleaners are robots. They can go around the room and then clean the floor at a particular time on their own. Okay, have their own path. They have sensors and they have some amount of AI. The other area is entertainment and laser robots. Entertainment like movies. So this is another area where it has come up even in India. We have a lot of movies in India which have robots featuring in them. Now, so we see that in terms of new industries, it is basically industries which have to do with the non-industrial applications, service, entertainment. Now, the question that comes up here is when we're talking about an industrial robot, where to use a robot? Can a robot be used everywhere? And then we'll go on to try and answer the question that what is the task that a robot cannot do? Now, this graph essentially shows the layout of the production system or manufacturing system. We know that in manufacturing, you can divide this manufacturing activity into this X and Y axis, in which the X axis is the production quantity. Okay, for example, cars. We produce a very large number of cars, say more than a lakh cars or 10 lakh cars of one type, but the variety of the cars could be less. So on the y-axis, we have product variety, so the different type of cars. So if you look at the this axis here, so we have mass production where the quantity is very large, but the variety is very low. Okay, so typical example is a car. So this is one side of your manufacturing spectrum. The other side of your manufacturing spectrum is a job shop where your number of parts is very, very small. Say, for example, here we may have only about 50 parts or 100 parts, but the variety would be very large. Okay, so this is called job shop production. And in between mass production and job shop production, we have batch production or what is called cellular production, where the number of production quantities would be about 10,000 and the product variety also would be large. Product variety would mean the different types of the product that you're producing. Okay, so for a car, what are the different kinds of cars that you're producing? Okay, so in this, so all of manufacturing fits in somewhere here. So depending on whichever industry you're thinking about, whichever industry you're considering, it would be fitting into this graph. Now, if you think a little bit where robots can be used, it would appear that you tend to say that it will come somewhere here. Okay, but that is not true. Why? Because there is other kinds of automation devices which are cheaper than robots. So normal automation is much cheaper than robots. For example, transfer lines, pick and place devices, then indexing devices. These are much cheaper than robots. Okay, and because you have a very large number of the product, there is no point in changing the program. So number one point is automation, other automation, or what we call hard automation, which is available, not robots. Number two is reprogram. So there is no point in reprogramming because it's doing the same task. So why use a robot? You can use a hard automation device. So in mass production, robots are used only for very specific applications. For example, spot welding is one. Okay, spot weld is one. Spray painting is another one. Okay, electronic assembly is another one, where the large number of parts are there and the task is of very large numbers. But it is not used extensively in mass production. So if you go to an automobile manufacturing company, you'll not find robots everywhere. Okay, and similarly, you'll find some humans still there. So this is a very interesting paradigm here. You'll find some robots and you'll find some humans, and in between you'll find hard automation. Okay, so mass production, some places robots are used, but not extensively. What about the other spectrum, job shop? Now, because in job shop the product variety is very high, you have to reprogram the robot. Okay, so you'll have to reprogram the robot repeatedly. As soon as your part changes, you have to reprogram it. And we'll see in subsequent classes on programming that programming a robot is very costly. Okay, because there are specialized people who do programming, and there are companies who do specialized programming. Because of which, if you keep changing your program, it takes time and the cost goes up. So robots are not used there. So if you're just going to pick up one part and keep from one place to another place, what is the point in using a robot? So if it cannot be used here and cannot be used here extensively, then this is the place where it can be used. So this is the place where robots are basically used in what we call batch production facilities or cellular manufacturing, where the number of variety is not very large, about 10,000. And after 10,000, you have to change the program and make some other part. The product variety is not very large. Okay, so that is where robots are economical. So we can see two aspects, the technical aspect and the economics aspect. In this graph, it is basically the economics aspect, that robots would be economical only if you are using them in this part of the graph and not everywhere. Now, this is basically what we call flexible automation also. So there is programmable automation, flexible automation, and fixed automation. This is also called hard automation. Okay, hard automation is basically mass productions. Okay, so mass production. Then this is job shop here. So somewhere in this region we use robots, and the basic reason being the question of reprogramming a robot. Okay, so if you have to reprogram it too many times, then it's not economical anymore. So it is economical if the production quantity is sufficiently large, at about 10,000, and there is some product variety. Okay, and you need to reprogram. So you cannot use hard automation here because you need to change the automation, which is expensive again. Okay, so you can use a device like a robot or an NC machine where there is the part quantity is sufficiently large and there is some part variety. So please keep this in mind, that do not try to use robots everywhere because they will lead to failure, economic failure. Now, the other question that we like to talk about is, what about the technology part? Can robots do everything? So this is an example of on the same lines. So flexible automation can be flexible manufacturing system. Okay. Now the robot cell design essentially consists of these three kinds of layouts. So we have a robot centered cell in industry, we have an inline robot cell, and we have a mobile robot cell. So robot centered cell will basically mean the equipment is arranged in a circle around the robot. This is what the name indicates anyway. So applications like die casting, arc welding, they use this kind of a robot centered cell, where the robot is in the middle and the machines are around the robot. In inline robot cell, this is the kind which is very commonly used in automobile industry. So in the automobile industry, so what we do see here is that there is a transfer line or a conveyor, and parts are coming on the conveyor, and at different stations the robots are doing different things. So this is automobile industry. So this is called inline robot cell, and this is one of the most commonly used in automobile and also in electronics. In electronics industry also exactly the same setup is used. The third type is a mobile robot cell. Now this is not basically followed because as per industrial standards, a robot should not actually move around because there would be human beings somewhere. So the human workspace and the robot workspace is different. That is something we'll see today in terms of safety. So this is another one where the robot can move around, but this is not normally preferred because of the problem of safety with regarding to humans. Okay. Now that brings us to the interesting question. We have seen where to use a robot, batch manufacturing. Okay, but then are there tasks which a robot cannot do? Now, whatever you have studied so far in terms of kinematics, dynamics, sensors, control, you have studied a lot. Okay, can you think of tasks which a robot cannot do? Okay, please take a minute to think. What kind of a task a robot cannot do? Or can a robot do everything? How would you answer that question? Okay, so one way of trying to answer that question is if a robot cannot do a task, why it cannot do that particular task? There has to be some reason. Okay, so think about it. I'm just coming to that in a minute. Now, the future of robotics is called general assembly, and such tasks come under what we call general assembly. Tasks which a robot cannot do, and because of which, if you go to the best robotics companies in the world, I mean not only robotics companies, industrial companies, automation companies in the world, anywhere, you'll always find that there are some human beings roaming around doing something. So what those human beings are doing, and is it that the company needs those human beings, or they are there because the robot cannot do the task? So it is not that the company needs those humans, because if they automate it, they save money, okay, in terms of bring down the cost of labor and things like that. As you understand very well, that a robot can work 24 hours a day. It doesn't need a break, okay? And they don't have to pay them insurance, and they don't have to pay them pension and all that. So for companies, they would like to automate all their jobs, but even the best companies are not able to do that because there are tasks which a robot cannot do. And those tasks come under what we call general assembly. Please think what they are. The second applications of future is cellular robotics. Many robots doing tasks together, multi-agent systems, space, underwater, unmanned aerial vehicle. This is something we talked about in defense applications, okay, where conventional soldiers and conventional warfare is being done by robots. Vehicles, this is another very, very big area of the future. We can call it robotic vehicle. We already have examples of Google car and unmanned taxi service. Surgical robotics, rehabilitation, safety in human-robot cooperation, designing of robots which are safe, bio-inspired robots, and then ethics in robotics. So this is the future direction in which the industry is moving. Now let's come back to the first point we talked about, general assembly. What kind of tasks a robot cannot do? Now, if I reverse the question and say what kind of task the robot can do, okay, for a robot to do a task, let me just draw it here. So a robot to do a task, like very simple task, like we have kept an object on the table and it has to pick and place it somewhere. So I have kept my table here, and I've kept sorry, I've inclined it. Let me keep it straight. So this is my table and this is my part. Okay, I've kept it there, and the robot has to pick it up. So that's a robot. It has to pick it up and then keep it somewhere else. Maybe take it up and keep it here. What is required? What is required is points in space, because as you understand, inverse kinematics has to do with points in space. So it is following a trajectory, okay, but these are points in space. Okay, so for every point, it will do inverse kinematics, get those thetas, and then give it to the controller, and the controller will drive it there. So if you want a robot to do a task, you should be able to define points in space. Okay, define points in space. So when we come to robot programming, we'll see this in more detail. The robots essentially in the program, they define points in space, and then we use commands like move and move it around and pick and place and do things like that. So if you cannot define points in space, then there's no way you can use a robot. Now, what does that mean? That basically means that if you're trying to pick up objects which are deformable, for example, like rubber. So if you define the point in a rubber sheet and you try and catch the rubber sheet, it will deflect immediately. So that point in space is gone, and the robot has no way of correcting it or knowing it. So this basically shows that wherever you cannot define points in space, you will have a problem in using a robot. And this is something we have seen, that about 20% of jobs are still not automated. And this is basically what is called general assembly, and this is the future of assembly. And this is where in companies, human beings are still required because robots can't do them. What are such tasks where you cannot define the coordinates? So wherever you're handling deformable material, rubber is an example, cloth, wiring. Okay, so in the automobile industry, if you go, you'll always find that there is this rubber which is attached onto the car body. So if I draw the car body here, so this is a car, if you can imagine a car here. Okay, so this is my car. So this is my the door. Okay, so we have the door here. Okay, so in the door, if you see, what you can see is on the door, if you open the door, you'll find that on the inside there is a rubber padding which is there. That is basically a seal which prevents water from getting in. Okay, so now this contains a rubber seal which is like this. Okay, this is a rubber seal. Now this rubber seal has to be inserted. How is a robot trying to insert it, or can a robot do this? Suppose I define this point and I define this point and I define this point. If a robot catches this point and tries to pick it up, what will happen? This will immediately deform. So these 2 points will change now. So the robot has no way of correcting that. So if you go to any automobile company today, anywhere in the world, you'll find that there is a human who does this assembly. So he'll take this rubber sheet, he'll put it in there, and then he's going to press it all along and then fix it onto the body of the chassis of the car. Okay. Then a wiring. When they're inserting the wiring, there is a lot of wires going through for the bulbs and the lights and the engines. So this wiring also is done by a robot and it is guided by a human. Okay, so if it is done by a robot, it's always guided by a human, because this wires, again, same example. So if there's a wire like this, if the robot catches it here and tries to pick it up, it will deform. And once it deforms, these points are not fixed. So these are applications where human beings are still required. Mounting of the wheel. Okay, so the wheel is mounted like that. So the wheel is carried by an overhead crane, and then the human being guides the wheel, fixes it onto the body on those four bolts which are there. Then he'll put the nut and then he'll tighten it. That's another one, something a robot cannot do. Very interesting thing. A robot cannot tighten a nut and a bolt very easily. Why? Because when you tighten a nut, you cannot define the points in space. What you cannot define the points in space? If the threads have set. Okay. So this is a very interesting problem in robotics. Please think about it, where you have a nut. Okay, so this is a nut and we have a bolt. So this is a nut and there is a bolt in there. Okay, so this is my bolt going through. So there are threads inside here. Okay, there are threads and there are threads here also. So how do you tighten the nut onto this bolt? So first you have to place it on that. Then you have to align the threads and then you can tighten it. Now what aligning the threads is is English language. How would a robot align the threads? Okay, there is no way of defining points. There is no way in defining trajectories here. Okay, so a robot will not be able to do this task, irrespective of how good it is. How does a human being do it? Please think about it. So the human would place the nut on the bolt, then he'll go in the anti-clockwise direction. And if you rotate it in the counterclockwise, anti-clockwise direction, what will happen is the nut will not tighten, but the two threads will set. The moment the threads set, there will be a sound. There's a very fine sound which you can feel or you can hear. And once the threads have set, then you go clockwise, okay, and then tighten it. So a human being would set the nut and then he'll use a power wrench to tighten it. So there are so many examples where a robot cannot do a task. Please think about it. And the general answer to that is wherever there is deformation going on, where the robot points in space cannot be defined, then there is no way the robot can do it. Cloth is another one. Okay, robot cannot handle clothes. It's very difficult for them. Same reason, if it tries to pick it up, it will deform. Okay. Smooth parts, light bulbs, glass like windshields and all, yes, but light bulbs and all, small light bulbs, it finds it difficult to do. Fragile parts. So these are parts which are difficult for the robot to do even today. So this is basically what comes under what we call general assembly. And the future of robotics is, can you make robots which can do general assembly? And there are companies which are trying to do that. And if you can solve any of the problems that I just talked about in terms of fixing rubber, then putting wires, then companies will pay you a lot of money. Okay, because as of now, there are no robots which can do that. Ethics and laws, this is the second part. Now, for human beings, we have laws, industrial laws, but what about ethics and laws for robots? So this is another area where robotics is not only confined to engineering, but we have legal, okay, we have social, we have psychological. So psychological aspects where people of different disciplines are trying to look at this new aspect of machines coming in contact with humans and trying to develop laws for them. Very simple example is if there's an accident in a company, then who pays? The robot pays or the human being pays? Suppose the human being is hit by a robot, then who pays? Okay, who's responsible? So there are no laws as of today, and basically what we're trying, the direction of the future is in trying to make laws for robot-human interaction, ethics. What about ethics of robots? Okay, very funny question, but this is there today. So there are companies which are trying to develop this ethical laws, laws for robots, legal issues, insurance, etc. Now, we have seen that Industry 4.0 essentially is to do with cyber-physical systems, which is we have computers and automation in third generation, which is 1970s. But today we have a connection between machines, humans, and AI. Okay, machines, humans, and AI together. Now, once there is humans in the loop, then this question of safety comes inside. Okay, so till now we were here, where we had automation, we have robots. Okay, and the protocol was the human and the robot. The human and the robot will stay in different spaces, so there is no question of safety. Okay, so they will not come in the same space, so they will not hit one another. But the moment humans and machines come together, then this question of safety comes inside, and this is where future robotics is going. Now let's look at industrial robot safety. This is where we are today. Okay, we have the human worker on one side who is here, and we have the robot on the other side, and there is a safety barrier in between. So if you go to any industrial application today, you'll find the robot is kept inside a cage. Okay, and the human is not supposed. The human cannot go inside the cage. That is as per industrial safety laws. These are laws. They have to be ensured. Okay. Now, if you do this, what happens is, if a task requires the human and the robot to work together, then it's not possible for both of them to come in the same workspace. So first the robot will do and then pass it to the human, then the human will do, or the human will do and pass it to the robot. So it's taking more time, double the time. So the future of robotics is essentially to try to make robots which are safe, where the robot and human can work together. So robot plus human can work together. Okay, this is the direction of so in terms of design new kind of robots. Let's have a look at this video. It will become more clearer of what we mean by this robot-human interaction.
On their heads. To start with, Baxter has a base cost of under $25,000 and can be programmed through a touchscreen interface without complex programming.
What's even cooler is that Baxter's movements can also be programmed by directly manipulating its arms.
Add to the fact that Baxter is armed with sensors to detect people, and you have a robot that doesn't need to be caged.
While Baxter is doing his part to bring automation to smaller industries, even larger, more expensive industrial robots are seeing major upgrades.
The new generation of large bots are being targeted to provide better speed and user-friendly interactions on their heads. To start with, Baxter has a base cost of under $25,000 and can be programmed through a touchscreen interface without complex programming.
What's even cooler is that Baxter's movements can also be programmed by direct.
So in terms of design, in terms of new designs for safe robots for interaction with humans, what is required is different approaches rather to this problem is to make robots which have joints which are soft or which are flexible. Okay, so if the robot has flexible joints, what would happen is, say I just give an example here. So I put a spring, a torsion spring onto the, so this is my link, and I put a torsion spring and I put another link there. So what would happen is there is flexibility or compliance in the joint. So if I were to hit this, or a human were to hit, or the robot were to hit a wall, what will happen? It will just go back. Nothing more will happen. So robots with soft joints are one that are coming into the robot-human interaction space, where the robot and the human can work together. If they work together, they save time. Now, social robots, of course, which are already living with humans, their design safety is paramount. So the conventional design we looked at in the last class is applicable only for industrial robots, not for social robots. For social robots, the first thing that needs to be done is make designs, use actuators and controllers which would ensure safety for human application with humans. Now, the second one is flexible link robots. So make links of the robots which are flexible, for example, like this. Okay, so we have links which are flexible. So if it were to hit, it can simply bend like that. Okay, so this is a flexible link robot. So these are ways of taking care of impact force and interaction with humans. Safety and control by using sensors or by in the controller itself. If the robot can figure out that if there is a human in front or it has hit with a human, then it should immediately go back, or it should limit the force there. So there are different ways of doing that. For example, torque limiters. Okay, torque limiters in motors. So if the motor torque goes up suddenly, it can figure out the armature current, and it can monitor the armature current and say that suddenly the torque requirement has gone up, so it must have hit something, so it can immediately stop there or go back. Okay, then there can be other ways of safety with sensors. So we can use different kind of sensors to sense if there is a human in front. Okay, so the new directions of robots for industrial applications is in interaction with humans. There are a lot of companies which are going in this area now and trying to develop robots which can be safe for interaction with humans. But as of today, industrial safety laws is still this: the human and the robot are in different workspaces. They should not come together. Okay. Now we'll look at few applications of robotics. We'll look at robotic welding and spray painting. Then we'll go on and look at robot safety. Okay, and then this is where robots are used. So we'll get an idea of what the design of robots involve in terms of industrial applications. So spot welding is basically creating a spot between two thin sheets in the car bodies. Now we know that car body, the chassis consists of angles and frames, but on top of that there is a thin sheet which is on top which covers the body. All right. Now to cover the chassis or to connect the chassis with the thin sheet, spot welds are done. Why? Because you cannot do heavier welding like arc welding. It will bend both the sheet and the body of the car itself. So majority of the spot welds in cars are done by robots. The second type of welding that is done is arc welding, where you are joining thicker sections. This is more in the case of railways, where you are using very heavy sections. Railway, shipbuilding is very common to use. So railways is one where you require very thick sections. Shipbuilding is another one where you require to use to weld very thick sections for using arc welding. Now this is an example of spot welding where we have the car's chassis, you can see, and there is a sheet at the side which is put onto the chassis, and there are multiple robots which are going and welding. So you can see that there are 4 robots here. They are going to different areas, and they are doing the spot weld and coming out. This is how spot welding is done. Now spot welding is very fast. It takes a few seconds, and if you can guess how many spot welds are required in a car, okay, just try and guess. It's as high as 2,000 to 3,000, and you'll be surprised that 3,000 welds in a car, and those are done in a few minutes only. And obviously human beings can't work at that speed and cannot go to difficult areas to do spot welding. Right? So we have multiple robots doing spot welding in complex areas, and they are just completing the task in a few minutes. 2,000 welds in 2 minutes. Now robotic spot welding started off around 1960s, and right from that time majority of the spot welds in the cars are done by robots only. And you can see this in any company in the world, any automobile company in the world. And the advantage being that it can do very large number of welds. Okay, so 30 welds per minute is very common. Nowadays they do it much faster than that. And the basic process of spot welding, as you might have studied in other courses in manufacturing, is that there is an electrode on both sides. So there is one side, we have an electrode here and we have an electrode there, and these are the 2 sheets. So there is one small thin sheet here, another sheet here, and a current is passed between them. And because of the heat generated in the center, because of this current, because of the I square R heating, what would happen is it will melt there. So because of the I square R heating in there, this will melt, and once it melts, it will get fused there, and that's your spot weld. Now the weld nugget is typically 6 mm or 10 mm in diameter. Okay, and the current range is very high. Current is past 3,000 to 40,000 amperes, and the welding time is as short as 0.5 seconds. So you can imagine that in less than a second it does a weld. Now, what is the advantage of this? The advantage is that it is fast, and many robots can do this very efficiently, but it does not deform the material, because you can notice that the weld is taking place in between the 2 sheets. So there is no effect on the other side. So on a car body, if you see, you will not be able to see the deformation because of weld, but the weld is there. That is where the sheet metal on the surface has been attached to the chassis. So this is what started off in this is what started off application of robotics in automobile industry, and even today spot welds are done by robots. Now the electron gun looks something like this. Okay, so there are two parts, and we have this sheet here and this sheet here, and it goes and catches it in this direction, and then it just passes the high current, and then you have a weld. Now there are different kinds depending on which direction you're welding. Say for example, the previous one is holding a sheet like this horizontally. This one can hold a sheet vertically. Okay, this fellow can hold it vertically. Okay, so depending on where you're doing the weld, how you're doing the weld, the configuration of the gun, electron gun, the electrodes, the tip of the electron gun can be configured. So robots normally would be having to do welds in all configurations, all angles. So they would have either kind of guns. Now the important parameters which are more towards the design of welding equipment is that the surface must be clean and smooth to optimize the bond, and it requires access on both sides of the joint. This is very important from robot programming, because you have seen the robot has to enter inside the car body, not hit another robot, not hit any part of the car body, do the weld and then come out. Now in terms of programming, so paths for spot welding should be such that they should not interfere with other parts to be welded. The robot should not interfere with other equipment or other robots, and the need for moving in straight lines for the welding gun, there is the move and the moves commands. So when we'll come to the programming part in the next class, we'll talk about the move and the moves command. So this is something very, very important, and this is very complex actually. So when we looked at the welding here, what we do see is that there are many robots which are moving in complex paths. So what is the inverse kinematic solution? So suppose I say I want to do a weld here. Okay, in that region I want to do a weld. What is the inverse kinematic solution? You have infinite solutions. So you have to find an optimal solution in which all the robots simultaneously can do all their welds in the release time without hitting one another and without damaging, without hitting any other part of the robot. Okay, so this is an extremely challenging problem. It is very clear from here that simple doing inverse kinematics for a path is not enough. Okay, so this is basically to show that finding the path for spot welding is extremely complex, and there are specialized companies which are doing that. Now, which types of robots can usually be used?